in the last few lectures, we had been looking at the AR model and the MA model in great detail. We have looked at the properties of this model and we have looked at how we estimate the parameters of this model as well. What we will do today is to combine the two models into a more general form, which is referred to as the autoregressive moving average model or the ARMA model in short. Now, the AR and the MA model actually comes out as special cases of this. So, we will look at the properties of the ARMA model, we will look at estimation methods for the parameters of the ARMA model, but most of this will borrow from what we have learned from the AR and the MA models. So, many of the results would actually extend to the two different components that we have here. So, you have the AR component and the MA component in the ARMA model, and the AR results would translate to the AR component of the ARMA model, and so would the MA component. We will be looking at these models, we will look at the estimation of the models, and finally, what we will be looking at is how we can extend the ARMA models to account for trend and seasonality. So, those are the final models that we will have in a Box-Jenkins setup, the ARMA or the SARIMA model. We will have a look at those models as well. Let us look at the autoregressive moving average model, or in short the ARMA model. An ARMA model is a combination of the autoregressive and moving average terms. So, we have xt, which is alpha xt minus 1 etcetera up to alpha p xt minus p. This is the autoregressive part, and we have epsilon t plus beta 1 epsilon t minus 1 plus beta q epsilon t minus q, which is the moving average part. So, xt is explained both by its own past values as well as the past and the present value of the innovations. As before, epsilon t's are white noise with mean 0 and variance sigma square, and we have two special cases here. The first of the special cases is that q is equal to 0. Then obviously, the innovation part is not there, and we have a autoregressive model of order p. Of course, epsilon t stays and it acts as the error in the model. On the other hand, we can have p equal to 0, in which case you just have the innovations and we will end up with a qth order moving average process. Now, we can write the model in short form as phi z into xt is equal to psi z into epsilon t. Remember that phi z is the characteristic polynomial and similarly is the psi z. For the MA component, psi z is equal to 1 plus beta 1 z plus beta 2 z square etcetera up to beta q z q, which really means that it is the characteristic polynomial which is similar to the MA model that we had. On the other hand, for the AR component, we have phi z similar to what we had for a AR model, and we can therefore write this as a combination of the autoregressive as well as the moving average part. As before, we will say that the process is invertible if phi z equal to 0 has all roots outside the unit circle. Remember that phi z is the MA component, and the MA process was invertible if its characteristic polynomial had all roots outside the unit circle. So, this extends easily to the MA component in the ARMA model as well. Similarly, we will say that the process is causal if phi z equal to 0 has all roots outside the unit circle. Again, phi z is the AR component characteristic polynomial part, and remember that AR model is causal if its characteristic polynomials has root outside the unit circle. So, again this translates to the ARMA model as well. Now, let us have a look at the correlogram, primarily the autocovariance or the autocorrelation functions. Let us look at a very simple case. Consider an ARMA 1-1 model, that is p equal to 1 and q is equal to 1. So, we have x t is equal to alpha 1 x t minus 1 plus epsilon t plus beta 1 epsilon t minus 1. Let us write z t as alpha 1 z t minus 1 plus epsilon t. Written in this form, z t would look like a AR process, a AR of order 1. We can in fact write x t in terms of z t. In fact, if we do this substitution, then we can write x t as z t plus beta 1 z t minus 1. So, we can get rid of the innovations epsilon t. Now, look at this very carefully. If we take z t itself as a innovation, then x t is now written in the form of a MA1. So, we can always do this, break this into two components. One looks like the AR1, which is the z t part, and x t looks like the MA1 with z t as the innovations. Now, once we do this and we calculate gamma star h as the ACF of z t. So, we will call gamma star h the ACF of z t, and as before we have gamma h as the ACF of x t. Now, if you do this, we can write gamma h, which is expectation of x t plus h, since x t has 0 mean. So, this would be the covariance between x t and x t plus h, and if we use the relation that x t is z t plus beta 1 z t minus 1, substitute this for x t as well as for x t plus h, that is x t plus h is z t plus h plus beta 1 z t plus h minus 1. And then we take the expectations with respect to the z variables now, and we will end up with gamma star h plus beta 1 gamma star h plus 1 plus beta 1 gamma star h minus 1 and beta 1 square gamma star h. Just very quickly, x t plus h means the first term is z t plus h, the covariance between that is gamma star h. Another term would be beta 1 z t minus 1 with z t plus h, and the covariance between those two would be beta 1 gamma star h plus 1, and similarly for the other two terms. So, we can express the ACF of x in terms of the ACF of z. But remember, gamma star h, that is the ACF of z, is sigma square alpha 1 to the power of h by 1 minus alpha 1 square. This is because z t is a AR1, and hence it has the same autocovariance function as a AR1 process. So, this would be the autocovariance function, and the parameter in this case is alpha 1. So, this is in terms of the autoregressive parameter of a AR1 model. So, we get gamma star h. Then what we have is, if we substitute this gamma star h in the previous relationship, we will end up with gamma h equal to sigma square 1 minus alpha 1 square into this term in the third bracket. Remember, there were 4 terms, and this 4 terms simplifies to these quantities. As a special case, let us take h equal to 0, and then we will end up with gamma naught, which is basically the variance of x t. And if we take h equal to 0 in the previous equation, remembering that h and minus h has the same impact on gamma, therefore, we get 1 plus beta 1 square plus twice beta 1 alpha 1 into sigma square by 1 minus alpha 1 square as the variance. And hence, the autocorrelation comes out to be a term like this. Now, what is important here is that if you look at this term, the first part is basically independent of h. So, you just have the constant alpha 1 plus beta 1 into 1 plus alpha 1 plus alpha 1 into beta 1 divided by 1 plus beta 1 square alpha 1 plus twice alpha 1 beta 1. So, there is no h here, but in the second part you have alpha 1 to the power of h minus 1. So, what happens is that as h becomes large, this alpha 1 being less than 1, remember that for the process to be stationary, we need the AR component to be less than 1. So, what happens is that as we increase the value of h, the term goes to 0, but exactly does not coincide with it. So, it becomes asymptotic to the h axis. This is what happened for the AR process. AR1 has a correlogram which shows that the curve goes down to the h axis, but never coincides with it. Now, generalizing this for a ARMA process, the ACF and the PACF are both asymptotic to the h axis and never become 0. So, it borrows from both the AR and the MA. Remember that for the MA, the ACF was equal to 0 beyond Q, but the PACF was not equal to 0 anywhere. So, it actually was asymptotic to the h axis. For the AR, it was just the reverse. The ACF was asymptotic to the h axis and the PACF becomes 0 beyond P. For the ARMA, neither the ACF or the PACF becomes 0 beyond P or Q. So, it becomes asymptotic to the h axis. There is another property that we would like to look at. If you look at phi z x t is equal to psi z epsilon t, that is the model, and if we invert the phi z, so we have x t is equal to phi z inverse psi z into epsilon t, and what happens is now we have a function of phi z inverse psi z, which would lead to basically the series in terms of b's. So, the b square, b cube terms etcetera would come, and what happens is that you have the epsilon t's and we will have the backward shift operators which will make them epsilon t minus j. So, this series actually on the right hand side would be an infinite MA series. So, an ARMA PQ can like the ARP written as a MA infinite series. Similarly, phi z x t is equal to psi z epsilon t. If we now invert the psi z term, then we write epsilon in terms of x t, and again expanding we can have x t minus 1 etcetera. Bring the lag terms to the left hand side and you land up with a AR process of infinite lag. So, the ARMA PQ can also be written as a AR infinite model. But then if we can write all three models one in terms of the other, why do you require so many models? The problem is that you cannot work with a AR infinity or a MA infinity model, because there will be too many parameters and will not be able to estimate an infinite number of parameters given a finite number of observations. So, basically what happens is that we would try and look at the orders to be small. So, there would be 2 or 3 models which would be very close to each other. Maybe a AR model with a high P would be very close to a ARMA model with very low P and Q values. In which case we would prefer the ARMA model, because we would be looking for what is referred to as parsimony, that is as few parameters as possible. So, the model which actually can be explained through a smaller number of parameters is the one that you would prefer. And although all the models are alternatives, so we can in fact choose the model which gives the best fit and has the smallest number of parameters. So, that is how we would be actually looking at alternative AR, MA and ARMA models. Now, when we have an ARMA PQ parameter, model. Okay. So, how do you estimate the parameters in this model? So, this is the model that we have, and we can write this model as x t is equal to phi b inverse psi b epsilon t, which can be written as an infinite sequence in terms of the epsilon t's. This is just what we have been saying now. Now, in this case, the relationship turns out to be psi naught equal to 1 and psi j is beta j plus summation of alpha j into psi j minus alpha I into psi j minus I, and this relationship we can work out for each of the j values, remembering that alpha I is equal to 0 for I greater than p, because we just have alpha 1 to alpha p, and similarly beta j is equal to 0 for j greater than q. Now, once we have this, let us truncate this infinite lag model to p plus q terms, and then use the innovation algorithm to estimate psi 1 up to psi p plus q. And then what we do is we take j equal to q plus 1 to q plus p. Then we can write 2. Remember that the betas won't come in here, because we are taking j equal to q plus 1 and beta q plus 1 is 0. So, the betas in the relationship would not come here, and we can write the relationship simply in terms of the psi's and the alphas. Psi's we have estimated, alphas are unknown, and we get p equations in this p unknowns alpha. And what we do is we solve this p equations to get estimates of alpha 1, alpha 2, alpha p. And once we have done this, let us consider I equal to 1 to q now. This is the first set of q equations, and for them we have the betas as well as the alphas and psi's, but the psi's and the alphas are estimated and we know them, and hence if you substitute them, we have q equations in the unknown betas which we can solve. So, this way we can solve all the parameters in the model. Let us look at another way of estimating the parameters. This is referred to as the maximum likelihood method. So, usual maximum likelihood, and you need to estimate the parameters assuming some underlying distributional form. We assume that the epsilon t's are IID, normal, 0, sigma square. In that case, let us consider the predictor y t hat of y t. Now, y t hat can be obtained as some combination of the past residuals. So, y t minus j minus y t minus j hat are basically the residuals at the t minus jth step, and we take a linear combination of this using theta I j's as the coefficients, and y t hat can be shown to be written in terms of this past residuals. Remember, we did something like this when we looked at the innovation algorithm in estimating the MA parameters. So, once we can do this, we can write the likelihood in terms of the residuals. The theta j's can be obtained using the innovation algorithm, as I said, and hence we can always get y t hats. And expectation of y t minus y t hat square is going to be sigma square r I, and we can write this, if we express it this way, the likelihood function as for the normal distribution. Look at this, the e to the power of minus 1 by twice sigma square into the sum of the residuals divided by r j. So, that is how we write the likelihood, and then we can solve this likelihood with respect to alpha, beta and sigma square. Remember, they are all embedded in the y j's or the x j's, and starting with values obtained by previous methods as initial values, we can iteratively maximize this. Now, there are two very important extensions of the ARMA model. The first of them is the autoregressive integrated moving average or the ARMA model. Now, what is the autoregressive ARMA model? This is given by phi b into 1 minus b to the power of d x t is equal to psi b epsilon t. So, you see, in this case we just have a new term, that is 1 minus b to the power of d. This is used, this model primarily is used for a process with trend. So, what happens if you have a trend? We generally detrend. How do you detrend? You difference. So, what we do is we difference first. So, difference the original series x t d times and we get z t. So, 1 minus b to the power of d x t gives us a detrended z t, and what you do after that is you fit the ARMA PQ model to this z t, and then you have a simple ARMA model. And if you put these two together, if you substitute z d by 1 minus b d to the power of d into x t, you get back to the single ARMA model, or the integrated moving average autoregressive model. Now, what is important about this is that we had been fitting ARMA models before, but ARMA models should be fitted to stationary process. In this case, if you have a trend, you have some non-stationarity, but you can remove the trend by differencing. So, what this does actually is the integration part is primarily that you are differencing to remove the non-stationarity and then fitting a ARMA model to the stationary model that you get. So, put together you can do it in a single step in a ARMA model. Similarly, there is another extension which is the SARIMA model. SARIMA is a seasonal integrated ARMA model. It is applicable when the process has both trend and seasonality. So, in this case, in addition to the trend, we have a seasonality component, and we write the model this way, where again 1 minus b to the power of d is used to remove the trend part. Differencing would remove the trend part. 1 minus b to the power of s whole thing to the power of d, basically this gives you, if you take capital D equal to 1, this would mean x t minus s. So, if you have a sth order seasonality or sth period seasonality, that would be removed by this component here, 1 minus b to the power of s whole thing to the power of d, and then you fit the usual phi b psi b for the ARMA for the detrended part, and the phi b to the power of s psi b to the power of s to the deseasonalized part, and you land up with what is referred to as a SARIMA model. So, the ARMA and SARIMA models are extension of the ARMA models. When you have, in the first case, when you have just simple trend, in the second case when you have both trend and seasonality. In today's class, we had looked at the autoregressive moving average model, or in short the ARMA model. The ARMA model is a extension, or rather a combination of the AR and the MA model, and we have seen the properties of the ARMA model. Most of these properties actually extend from the AR or the MA model. We have also seen how to estimate the parameters of the ARMA model using partly techniques that we have used for the moving average model in general, the innovation algorithm as such. We also saw that if there is non-stationarity in the model in terms of either the trend or seasonality, then how we can extend the ARMA model to account of this. So, we will also looked at or suggested how we can look at the ARMA, and if necessary to the seasonal ARMA or the SARIMA model as such.